Okay. And democracy, I think that your phone is not muted. Okay, I will mute, but of course you can open it if you want. And I will also share my screen with you all. I just need to open. Oh, let me just open the file first, okay? Because I think that I didn't. Oh, no. Oh, it's this one. Okay, so I can share. Now, let's share screen. Share entire screen. Great. So, mhm. Okay, guys. So we already saw some horizons like the Causic horizon, Cryic, Celic, or not. I think that maybe, yeah. We already saw these horizons, right? The horizons that could be organic or mineral, like these ones, the Causic, the Cryic, the Celic, the Thyonic. Those are all only organic horizons as the folic and histic horizons. Those that could occur at surface and are only mineral, like the molic and the churnic. And this is quite interesting because you should remember that in soil taxonomy, we have only one horizon associated to this preservation of organic matter due calcium and organic matter interaction. That's what we call molic apatom. In the WRB case, in the WRB, we split this interaction between calcium and organic matter in two possible diagnostic horizons. We call it as molic and churnic horizons. And the molic horizon, it has very similar properties to the molic pattern in the soil taxonomy, but the churnic horizon, it's a, let's say, special molic horizon. We have darker colors, we have thickers. So we have a thicker horizon, and we also have a higher content of organic carbon. Okay, so we have the molic and churnic horizons in WRB, but in soil taxonomy, we just have the molic pattern. We also saw the umbric horizon. That's a horizon that also could host a high content of organic carbon, but in this case, the umbric horizon is not formed by interaction between calcium and organic matter. In this case, we have more interaction with aluminium and also clay minerals with the organic matter. So we know that we have a lot of processes that could form a horizon that has dark colors and high contents of organic carbon. As I read said, we have some horizons, as for example the churnic and the molic, that we have specific interaction between calcium and organic matter. This interaction between a metal and organic matter could reduce the decomposition of the organic matter. So the microbiological activity, it's lower because of this interaction, and this yields the formation of a thicker, darker, and carbon-rich horizon. That's called molic or churnic according to the content of organic carbon, according to the thickness, according to the color. Okay, this process is quite common in the world, especially in soils formed from limestones, basalts, and mafic rocks. Rocks and conditions, climate conditions also are quite important that yields a high content of calcium in the soil. So let's say that, for example, I have a climate condition that's not dry or not too dry to leach all the calcium in the system. So I have a soil that steals with high content of calcium because of the chemical warfaring. The chemical warfaring and the leaching is not so intense, and because of this, I can form some horizons that has high calcium content, okay, exchangeable calcium content. This high exchangeable calcium content could create some interaction with the organic matter, and this yields or this reduce the microbiological activity. This is quite common, as I said, in soils that are formed from weathering of limestones and other calcium-rich rocks, and also they are more common in chemical conditions that induce less weathering and less leaching as dry climate conditions. So they are quite common in arid and semi-arid climate conditions because these areas, they has less weathering and less leaching. But in wet zones, in wet areas, we also can find horizons as this one that has dark colors and also a high content of organic carbon. In these areas, the intense weathering and leaching reduce the calcium content, the exchangeable calcium content, but steals a high organic carbon content. And why? Well, because in this case, it's not the calcium, but the aluminum that could interact with the organic matter. In these conditions, the high content of aluminum in acidic pH, in acidic soils, could reduce the microbiological activity. And because of this, you can find a soil with a higher organic carbon content and darker colors. Okay, so in the unbreak horizon, it's quite common that now we have acidic conditions with a high aluminum content that also reduces the microbiological activity. And also the clay content, it's quite important in these cases, especially because of the bioturbation, because termites, ants, and other animals, they induce a higher aggregation and stronger aggregation, and this stronger aggregation reduces the physical contact of the organic matter. So the microbiological activity cannot physically achieve the organic matter. And because of this, you also produce higher, or you can stock more organic carbon that could produce an unbreak horizon. Okay, you already know that. I'm just highlighting these conditions. And we just start to saw the horizons which concentrates matter. And horizons which concentrates matter are horizons that are subsurface horizons. We started with the Argec horizon because it's quite important here. And we saw that the Argec horizon is quite similar to the Argelic and Candic horizons. Okay, so now we have the opposite. In the soil taxonomy, we have two diagnostic horizons. We have the Candic and Argelic. Both could concentrate clay at subsurface horizons, okay? Both could register this higher clay content than the overlying horizons. But in the WRB, we just have one. So we mix the Argelic and the Candic horizons in the soil taxonomy in the same horizon that we call Argec horizon, okay? And the Argec horizon, it could express clay alluviation or not, no problem, okay? The Argec horizon express a higher clay content than overlying horizons, and sometimes it also could express clay alluviation. You can see the features produced by clay alluviation or not, no problem. But the Argec horizon, it registers a higher clay content than overlying horizons, okay? So we already saw all the characteristics, and I highlight them a lot. That first of all, you don't need to memorize everything, guys. Don't worry about that. Okay, you just need to understand that we have different criteria. Okay, of course they are relatively similar, okay, but the values could change and they change. So it's not a problem when you try to classify a soil that you check the brochure. Okay, you check the PDF file with the WRB and soil taxonomy and check if you are doing the correct classification. Okay, don't worry about that. You must check them. I always check them. A lot of people, even the people that writes this kind of document, they check because it's quite hard to memorize everything. So don't worry, you don't need to memorize. What it's much more important, it's important that you memorize that the Arctic horizon registered higher clay content than overlying horizons. And we have some criteria to identify this. And some of these Arctic horizons, they also could express clay elevation features. For example, clay skins that are really, really common, and they express the migration of clay, okay? So, as I said, some of them could register alluvial clay, some clay bridge, clay coating, clay skins, anything that express this migration. And I already show you some photos that express this, especially the clay skins. They are quite easy to see in the field after you have some training, okay? And I also said that this arch horizon, it's not part of a netrec horizon and not part of a spodec horizon, okay? Because they are, let's say, we have some priorities in the classification. And because of this, if you call a horizon as a netrec horizon, it could not be called as an argic horizon, okay? Because the netrec horizon, let's say that's more important. Why I'm saying that's more important? Because the netrec horizon express more complex process, okay? We will see in the next few slides. This netrec horizon express that the soil suffered by other kind of process, not only clay alluviation or clay destruction or clay production or elutriation. And because of this, it's more important to consider another name, another diagnostic horizon, okay? This spodec horizon is the same, but the spodec horizon, we have just one exception, unless alluvial clay is evidenced. Okay, so if you have some features that express clay alluviation, so in this specific case, you can have both. You can have spodec and argic horizon at the same time in the same depth. This is quite important because some people does not realize that sometimes you have this to have more than one diagnostic horizon in the same depth. Okay, this is not a problem, guys, for soil taxonomy and also for WRB, but especially for WRB, because sometimes you can find this horizons that fit the criteria for more than one diagnostic horizon. So if it's not clearly that you cannot have this combination, like here, for example, you don't have this combination of netric and argic horizons, you must combine them. You must classify that you have both, okay? So again, you only cannot combine the argic with netric and argic with the spodec unless this section that you are trying to classify as an argic horizon also has features that express clay alluviation. So in this case, you must classify as an spodec horizon and also as an argic horizon. Okay, I think that the results will be much more interesting to see this, and then you can understand even better. Okay, and also we saw that the argic horizon could be composed by lamella and this also change the thickness. Okay, so the thickness of an RJ horizon could be 7.5 centimeters or 15 centimeters according to the texture of this material and which is the composition of it. Okay, so if you register sandy texture or sandy loam textures, so in this RJ horizon the minimum thickness is 7.5 centimeters. But if you have any other kind of texture, finer textures like clay textures, so in this case, you need 15 centimeters, okay? If you have lamellae. We already saw the lamellae in the SOIL taxonomy, so if you cannot remember very well, are those horizontal layers that are rich in clay, and they seems like some horizontal horizons that express this higher clay content. You must just check again our slides or check again our videos, and you can see and understand even better this lamellae, okay? Oh, I already put a photo here, so you don't need to do that. The lamellae are those reddish horizontal layers. Okay, so you need to combine the thickness of them. Do you remember? So you need to consider that if I register like 10 lamellae, I need to combine the thickness of all of them. And this is an RJ horizon, let's say a more classic RJ horizon without this lamellae, okay? So you need to consider the minimum thickness of 7.5 or 15 centimeters according to the presence or absence of this lamellae and the texture of it. So now let's see a metric horizon. In the metric horizon, it's, let's say, a special RJ horizon. The metric horizon also express a higher clay content in the subsurface horizon, but in this case, the metric horizon, it's more related to salt, especially sodium presence. So in some very dry conditions, in some climate conditions that induce salt precipitation. For example, let's say that we are planning to go to a arid area, and in this arid area, it's quite common to see some salts in the surface, and then not only on the surface, but also present in the soil, inside the soil, okay? Okay, so when it starts to rain, the water dissolves the salt, and the salt yields the chemical elements. So if the salts are enriched in sodium and or magnesium, these two elements, they induce chemical dispersion. So this chemical dispersion could destroy some aggregates. And the destruction of these aggregates yields the clay that before composed these aggregates. Now this clay could migrate according to the gravity and according to the water movement. And then the clay starts to migrate from the surface horizons to the subsurface horizon and concentrate at the subsurface, okay? Especially on the top of the pads. So this metric horizon, it's quite common that you register high clay activities. And these high clay activities, because of the shrinking and swelling, they produce prismatic structures like these ones that you can see. They produce structures that register a high vertical axis and at least a higher vertical axis than the horizontal one. Okay, so this high vertical axis, they are called prismatic structures, but because of the clay migration, you have some filling of clay between two aggregates and also on the top of these aggregates. And this clay migration induced the formation of a convex shape. Okay, this top now has a convex shape. And why? Because we have the infilling of the voids and only on the top, but even then here on the voids, we have some water migration. It's quite slow, but even then, you have some water migration. And this water migration could erode some clay that's on the top. This slightly erosion induce this convex shape because now you erode more clay from this edge than the top. Then this convex shape now change the type of structure. We call it as columnar structures, not more, we don't call it more or less prismatic structures. So now the prismatic structures, they change, they need be reclassified as columnar structures. They are reclassified because the top is not flat anymore, but has a convex shape. You can easily see this change on this area where I'm showing with the mouse. So in this aggregate, in this pad in the middle, you can see our original structure that was the prismatic one with this yellowish color. And in this zone with this whitish color, you can see the clay which migrates from the top and concentrated on the bottom on this subsurface horizon. So all this zone, this whitish zone, it's just clay which migrates from the top and concentrated in the voids and especially on the top of the aggregate. Okay, so high sodium, exchangeable sodium concentrations could induce the chemical dispersion of aggregates and induce, because of this, an intense clay movement, an intense clay migration from the top to the bottom. It's why we said that, yes, we have a higher clay content at the subsurface horizon, but this process, let's say that it's more complex than just clay alluviation that we can see in other areas and forms the Argent horizon, okay? The Natrec horizon, it's quite common in dry lands, in areas that we don't have a lot of water, because this low amount of liquid water could induce the salt precipitation and then the chemical dispersion, okay? These natric horizons, they are commonly high activity clays, as I said. They are commonly eutrophic. We have much more bases than aluminum. It's much more common in low wafting and low leaching conditions, okay? They have this kind of columnar and prismatic structures, and because of this higher clay content and the presence of prismatic and columnar structures, the water penetration through the soil is really, really slow. So the water migration, the water percolation, the water conductivity, it's quite low. And the penetration of roots are also quite difficult, because these soils, they present, these horizons, I'm sorry, they present a very high bulk density, like really high, guys, like 1.6, 1.8 sometimes. And this is not a compacted, this is not a horizon that was influenced by humans, it's natural, okay? This horizon, it registers a high, very high bulk density, just because of this intense clay migration from the top to the bottom. And this natric horizon is also quite interesting, because you can see it registers some darkish colors. It's quite common that the natric horizon present darker colors than the surface horizon. Why? Well, after this chemical dispersion, these aggregates, they are destroyed and the clay could migrate, right? But not only mineral clay, organic clay also could migrate. So the organic matter also could migrate from the top to the bottom and concentrates at the subsurface horizon. It's not a very high organic carbon content, okay, but it registers some concentration of organic matter, at least higher than the overlying horizons. And because of this, you can see the darkish color. And also the nitric horizon, it's also quite common to host a perched water table. Because of this very, very low water conductivity, sometimes the water could concentrate on the top of this nitric horizon and starts to reduce some iron oxides. And because of this, you can register some grayish colors. Okay, so you can see that the nitric horizon is quite different from the argic horizon. The only thing that they have in common is in both cases we have a higher clay content, but let's say that the nitric horizon, it register less aggressive or a less a more aggressive, I'm sorry, a more aggressive or a more complex and complicated condition. Let's say that it's much more difficult to manage a soil with a nitric horizon than an argic horizon, because the nitric horizon, you need to consider that you register a high sodium content, a high electrical conductivity, you register a higher clay content at the subsurface, you register some salt precipitation, you register some perched water table, you register a low organic carbon content at the surface. So you register a lot of several issues and problems that you need to solve, and you need to consider them during the land management. So it's not something like, oh, I just have more clay content at subsurface. No, you have a lot of physical and chemical problems that now highlights that this horizon is quite complicated. This horizon needs more attention than several others. Okay? You can see here another nitric horizon, in this case with a prismatic structure. So you don't register on the top of the structures on these pads this convex shape, only the flat surface. Okay, so this flat top, it's more related to prismatic structure, but still the nitric horizon. You can see that it's quite easy, quite easy to see, to identify the difference between these overlying horizons and the nitric horizon. Okay, just because of this very high difference of chemical and physical soil properties, and of course also morphological properties. So let's see the criteria to identify a nitric horizon. Okay, the nitric horizon is composed of mineral material, and it register a texture class of loam sand or thinner than this, and at least 8% of clay. So I could not register a sandy texture, and I could not register less than 8% of clay. Okay, this is the first criteria. And we need to fit also number two, at least one of it. Okay, one or both of the following. Letter A has an overlying coarser texture layer with all of the following. First, the coarser texture layer is not separated from the nitric horizon by a lithic discontinuity. Okay, so this difference of clay content between the nitric horizon and the overlying horizon is not formed, for example, by alluvial materials. So it's not something that was produced by a river. It was something produced by salt concentrations, salt dispersion, chemical salt dissolution. I'm sorry. So salt precipitation, salt dilution, and aggregates destruction, clay dispersion, clay migration. Okay, so it's a more complex process than just the river depositing some clay-rich material and then after that some sand-rich material. So these differences that are more related to differences of parent material, that are more related to colluvial and alluvial materials, they are called lithic discontinuities. Okay, so if you register a lithic discontinuity, you cannot register a nitric horizon. The difference of chemical and physical properties, they must be connected, they must be related to some process that express this clay migration. Okay, and if the coarser texture layer directly overlies the nitric horizon, so its lowermost sublayer does not form part of a plot layer. So this coarser layer is not coarse because of the human action that makes the material and destroy the aggregates and the pads, and because of this they induce some clay migration. Okay. Number three, if the coarser texture layer does not directly overlie the nitric horizon, the transitional horizon between the coarser texture layer and the nitric horizon has a thickness equal or less than 15 centimeters. Okay, so if I register the nitric horizon and something overlay of it that register a coarser layer, the difference, the distance between them should be equal or less than 15 centimeters. You need to memorize, not, you don't need to memorize, but you need to remember that in the soil taxonomy, this thickness could be 15 or 30 centimeters, according to the Argic and Candic horizons. So here we just have 15 centimeters. Okay. Number four, if the coarser texture layer has more than 15% of clay, the nitric horizon has 6% more clay, okay, or less than, or more than this coarser overlying horizon. Okay, so if the coarser texture has less than 15% of clay, the nitric horizon should be 6% or more enriched in clay. Let's say, for example, let's say that we have an A and a B horizon, and this A horizon has only 10% of clay. So in this case, the coarser texture layer has less than 15. In this case, the nitric horizon should be 6% or more enriched in clay. So if we have a horizon with 10% of clay and a B horizon with 20% of clay, so okay, we have at least 6% more. So we have a nitric horizon. If the coarser texture layer has between 15 and 50% of clay, so the ratio of clay in the nitric horizon to that of the coarser texture layer is equal or higher than 1.4. In this case, you also can remember that soil taxonomy, they use 1.2. So we have, let's say, more criterials here, considering that if I split the clay content of the B horizon and this A horizon or the E horizon that overlies the B horizon, the difference between them, the ratio between them should be at least 1.4. Okay, if the coarser texture layer has 50% of clay or more than this, then the nitric horizon should register 20% or more clay than this overlying horizon. So let's say that, for example, I have an A horizon with 60% of clay. To identify a nitric horizon, this nitric horizon should register at a minimum of 80% of clay, because it's at minimum of 20% more. Okay, so you see that the criteria, it's basically the same for the Argic horizon. Okay, it's why we call that a special Argic horizon. Okay, but in this case, we fit this and other properties. Which others? Well, we also could register some features that express alluvial clay. Okay, for example, clay bridges, connecting some sand grains, at least 15%, clay coverings, covering some aggregates, some pads, some pores fragments, or even biopores. It's at a minimum of 15% too, or we can see some features in thin sections that also express this clay migration, okay? Number, number 4, a ratio of fine clay to total clay in the natural horizon greater by at a minimum of 1.2 times than the ratio of the overlying coarser texture clay. As I said, some people, they extract the fine clay that's is the smallest fraction of clay, and they split the content of fine clay and total clay. So you must do this for the possible metric horizon and for the overlying horizon. If this difference between them it's equal or higher than 1.2, so then you can register a metric horizon. Okay, you must fulfill at least one of these numbers and has one or more of the following: a columnar or a prismatic structure. So a columnar or prismatic structure are morphological features that I already showed. You must identify one of them, or an angular or subangular block structure and penetrations of overlying coarser texture layer in which there are uncoated sand and or coarse silt grains extending to more or equal to 2.5 centimeters into the metric horizon. So you can see some penetrations of this material into the metric horizon, this coarser texture layer, okay? And they should be uncoated sand or coarse silt grains, okay? If you register this angular or subangular block structure. Something that's much more connected to this metric horizon is the presence of sodium. Remember, the exchangeable sodium. So the exchangeable sodium percentage should be equal or higher than 15. JJ, how could I calculate this exchangeable sodium percentage? It's quite easy. You just need to split the sodium, exchangeable sodium, by the CEC and then multiply this for 100. So the result will be exchangeable sodium percentage. If it fits to at a minimum of 15%, in the entirely metric horizon, or at least the first 40 centimeters, okay, sorry, okay, I have a metric horizon. Or both of the following. Number 1, I have more exchangeable magnesium plus sodium than calcium. Okay, so I just need to compare the content of magnesium, the content of sodium, and the content of calcium. If I sum magnesium and sodium, and this sum it's higher than calcium, so it could be okay in entirely metric horizon or in the first 40 centimeters of the metric horizon, and an exchangeable sodium percentage of 15% in some subhorizon starting in a distance lower or equal to 50 centimeters below the upper limit of the metric horizon. So in the first 50 centimeters of this metric horizon, I should register a minimum exchangeable sodium percentage of 15% in at least one of the subhorizons. If I can see like B1, B2, B3, one of them should register a minimum exchangeable sodium percentage equal or higher than 15%, okay? And of course, I need to consider that this 15% should be fulfilled in the first 50 centimeters, okay? And I need to register a minimum thickness, okay? The minimum thickness here varies according to the texture of the metric horizon. If the metric horizon has a texture of sand, loam, or thinner, So it will be 7.5 centimeters. If I register other kind of textures, like a sandy texture, could be 15 centimeters, should be 15 centimeters or higher than this. Okay, so two options of thickness. Let's say loamy and clay and silty textures, 7.5, sandy textures, 15. Okay. So great. We saw a special type of Argec horizon, which express a higher clay content than the overlying horizon, but also express some sodium concentration, columnar structure, some specific properties that are quite related to the process which creates this natric horizon. Let's see now other horizon, okay? Another horizon that also express some clay migration, but now express organic clay migration, especially organic matter, also could migrate in sandy and sand-rich materials, some sandy horizons. They could express some clay migration, some organic clay migration, and this organic material migrates and concentrates at subsurface horizon. The spodec horizon, it's also quite similar to the spodec horizon in soil taxonomy. They have similar properties. Again, we always must be sure and reclassify each horizon. We cannot just translate between one horizon into another one. We must check the criteria, okay? But they are quite similar. Both express what we call pluvialization. That's this kind of migration of clay, organic clay, and sometimes aluminum and iron from the surface to subsurface horizons, okay? These spodec horizons, they are quite common in several climate conditions. They could be found in temperate, tropical, equatorial, polar conditions, no problem, but they must be associated to sand-rich materials and flat surfaces, okay? So they must be connected to flat surfaces that induce the water migration through the surface, from the surface to the subsurface horizons, where we can have this concentration of organic matter, okay? So we already saw these pictures showing some spodec horizons that express this migration of organic matter and also aluminum and also iron concentrating and forming these spodec horizons. The criteria for them, we must register an acidic pH because these soils, they are connected to this intense wafting and leaching. So the pH must be acidic, must be low, or at least lower than 5.9, unless the soil was affected by humans. For example, if we added some lime or if the soil was fertilized, okay? And it's registered a subhorizon with an aluminum extractable by ammonium oxalate value. So this is AlOx is the aluminum content extractable by ammonium oxalate. So ammonium oxalate only can dissolve low crystalline aluminum, and especially aluminum that's connected to the organic matter. So it's why we use this aluminum content extractable by ammonium oxalate as an evidence of the spodec horizon, because it could shows you that, oh, we have a strong connection between organic matter and aluminum. So this strong connection induced a migration of organic matter and aluminum, and both migrated from the top to the bottom and concentrated in the spodec horizon, okay? So it should register aluminum value that's equal or higher than 1.5 times higher then the lowest aluminum content extractable by ammonium oxalate value of all mineral layers above the spotted horizon. So when I compare the aluminum content between the spotted horizon and these overlying horizons, this content in the spotted horizon should be 1.5 times equal or higher, okay, than this. And it has in the uppermost 1 centimeter, one or both of the following. At least 0.5% of soil organic carbon, or a menstrual color chroma that's equal or higher than 6 when moist in 90% or more of the exposed area. So in the first 1 centimeter, you should register a minimum content of organic carbon or a darkish color or I'm sorry, reddish color or yellowish colors. Okay, because when you have a chroma that equal or higher than 6 means that this color it's quite intense. Okay, so you have a very strong reddish color or a very strong yellowish color like this ones, for example, which express the migration of aluminum and iron. Okay, so the two options is that in the first centimeter, register at minimum 0.5% of organic matter, or you must register strong colors, very high chroma. Okay, and it has one or more subhorizons with the following menstrual colors: moist in 90% of this exposed area, so the dominant color, a hue of 5YR or rather than this, or a hue of 7.5, I'm sorry, 7.5 YR, and a value that's equal or below 5, or a hue that's 10 YR and a value and a chroma that's equal or below 2, or a hue of 10 YR and a chroma that should be the minimum of 6, and or I'm sorry, a color of 10 YR that it's 10 YR 3/1. So very, very strong colors, but with a dark color, or a hue of N and a value that's equal or below 2. So these are the options. You must check them. It's a lot of things to memorize. And one or more of the following. This spotted horizon is overlaid by cleric material that's not separated from the spotted horizon by a lithic discontinuity. So again, we must identify that this spotted horizon is below something that register a very whitish color that's connected to sand materials, and this difference of morphology could be not related to lithic discontinuity. So the difference of the morphology between these two horizons is not something related to alluvial and or colluvial materials, okay? Or the minimum of 10% of the sand grains of the horizon show cracked coatings. So I should register some organic coatings covering the sand grains, and they should be cracked. Okay, we must see some cracks. This is much more easier to see. This is easier and much more common to see in the fixed sections, not at the macroscopical morphology. Okay, but yes, you can see them in some rare and special cases. Or it should register a subhorizon that's cemented with a cementation class of at least weakly cemented, so at least a weak cementation in 50% of this horizontal extension. So I should register that this spotted horizon should be in some way hard or cemented, so I cannot easily broke it. And this cementation, it's quite connected by the aluminum, iron, and organic matter. When we have I'm sorry, guys. When we have a strong cementation of material, it's connected to a strong migration of organic matter and iron and aluminum. Especially iron and aluminum, they usually migrate in flooding conditions. So because of the soil that has a sandy texture, water is penetrating through the soil. This water could reduce the iron, and then iron too could migrate. The aluminum also could migrate with the organic matter. And when they achieve a position that they are not migrating anymore, they start to form the spotted horizon. So this horizon could suffer some of dehydration, so you can lose some water. And because of this water is being lose it, you have more oxygen that could oxidize the iron. And because of this, this iron can start to cement a little bit the soil. So the soil, it's partially cemented, at least weakly cemented, as we can see. And hardly you can break it with your knife or with your hands, okay? So this cementation, it's connected to the iron, which migrates with the organic matter. We also have another option that we register a subhorizon with an aluminum content extracted by ammonium oxalate plus half of the iron content also extracted by ammonium oxalate, value of equal or higher than 0.5%. That is 2 times higher or equal that of the lowest aluminum content and half of the iron content value of all the mineral layers above the spotted horizon. So I need to run this kind of analysis, ammonium oxalate. I attack the soil with this ammonium oxalate that extracts the aluminum and iron content that are deeply connected to the organic matter. And then after some analysis, I need to compare the content in the spotted horizon and all the overlying horizons. And according with these contents, I can fit this criteria, okay? And the spotted horizon does not form part of the network horizon. So you can see that here they are not the same thickness. And the minimum thickness to identify a spotted horizon is 2.5 centimeters. So I cannot identify on spotted and network horizons in the same depth. And the minimum thickness of the spotted horizon, it's only 2.5 centimeters, can be very, very thin. Okay. Now let's see the sunbreak horizon. And the sunbreak horizon, it's quite interesting because it was formed by also clay migration. So we have some clay migration from the top to the bottom. And this clay migration, it's essentially organic matter again. But this sunbreak horizon, it's not connected to sandy rich materials and also not connected to sodium sodium concentrations. So I can see, for example, in this specific photo, close to 30, between 30 and 40 centimeters, a darkish color, and this darkish color, it's a sunbreak horizon because it's not something that's connected to aluminum migration or iron migration or sodium content. So the high sodium content could induce the formation of the network horizon. It's not this case because the sodium content is quite low. The aluminum and iron migration could register this organic matter migration in sandy materials that forms the spotted horizon. It's not this case because the sodium or the aluminum content and the iron content extracted by ammonium oxalate, it's quite low, and this is not a sandy material. So in this case, we have a sunbreak horizon. Okay. The Stormbreaker horizon is not very well understood until now. We still have some studies that are trying to explain its formation. And for now, we have two big theories that try to explain the genesis of Stormbreaker horizons. Okay. The first one says that the Sunbreak horizon is a residual surface horizon formed in water past conditions. Okay, so let's think, for example, that this soil, it was formed in the past in water past conditions. So it formed, for example, an umbric horizon, okay, with a very thick horizon, surface horizon, that reduced to darkish colors, that reduced to strong reddish or yellowish color now, and register some high content of organic carbon. So I register a horizon that in the past was formed by water conditions, so with high organic carbon content, darkish colors. But then after some time, after the formation of this umbric horizon, we have a change, a switch of climate conditions. And this climate change induced a new vegetation cover. So in the past, with the wetter climate conditions, we could register, for example, forests. And now with drier conditions, we can see some shrubs or even some savannas. The addition of organic carbon, it's less than before, and we could register even some erosion of this horizon, this surface horizon, and also some microbiological activity that could decrease the content of organic carbon, because now we have less addition of organic matter, and the microbiological activity can destroy some of this organic matter, and with the lower addition, the horizon, the surface horizon, is getting less darkish, now assuming a yellowish or reddish colors, or at least less brown, less dark. Okay, so the surface horizon starts to lose some organic carbon and lose this darkish color. But at subsurface level, this darkish color, this organic carbon, it could be preserved because you are quite far from the surface. So the microbiological activity is lower at these depths. The microbiological activity, it's always, or at least in the majority of cases, like 99% of the cases, it's highest at the surface and decrease according to increase of depth. So at a high depth, this microbiological activity is quite low. And because of this, even after the climate change, you can preserve some organic matter. You can preserve some darkish colors. So some people, they said that the sunbreak horizon is an evidence of a past thick and carbon-rich organic horizon or mineral horizon, but at least a horizon that was carbon-rich in the past. Okay, but because of some change, some switch in the landscape, especially because of climate change, we destroyed the darkish colors at the surface. We destroyed this high organic carbon at the surface, only at the surface. And at the subsurface, we preserved this organic carbon and these darkish colors. Okay. Well, this is quite interesting. I like this theory a lot, but as I said, we still need to understand this better. So a lot of studies, they are still running, trying to prove, to show that this theory is correct, that this is the way that we can form some sunbreak horizons, okay? Another theory, they just said that the sunbreak horizons, they express clay migration, organic clay migration, especially without the presence of features that express this clay migration and without the high aluminum or sodium content connectors. Okay, so it could be another process that we still don't know, at least we still don't understand very well, that could express this clay migration. But as I said, still in process. We have a lot of people, a lot of soil scientists, researchers trying to understand better this process, trying to understand how the sunbreak horizons are formed. Okay. The criteria for it, of course, could not be a lot because we still need more information. So a sunbreak horizon is a mineral material. So the organic carbon content should be below 20%, but should be equal or higher than 0.2%. And it should register a content of organic carbon that it's equal or higher 25% in a relative way and 0.2% in an absolute way than the overlying layers. So when I compare the organic carbon content in this specific horizon, it should be higher than these overlying horizons. How much higher? 25% in a relative way and 0.2% in an absolute way. So I just need to compare the contents, okay? And does not have a lithic discontinuity and at its upper limit and does not form part of a natric or spodic horizon. So I cannot register natric and spodic horizons connected to the sunbreak horizon. Okay, as I said, it is another process. Okay, it is another process not connected to sodium or aluminum. Okay, and it should register a minimum thickness of 10 centimeters. Okay, so these are the criteria for the sunbreak horizon, but in my opinion, still a lot of gaps. So we need to understand much better this sunbreak horizon. Okay, I just saw one sunbreak horizon. That's this photo that I showed you in my entire life because they are quite rare and people still working on them. We also have the petroplintic horizon, and the petroplintic horizon is a horizon that it was cemented, strongly cemented by iron. So we have a horizon that hardly you can broke with your shovel, with your hammer, with your knife. Okay, this petroplintic horizon is deeply cemented by iron. It's quite common in the tropics. Okay, for example, here in Brazil, we can see a lot of them, like a lot. Okay, they register this reddish color because of the iron, and the roots hardly can penetrate through it because, as I said, it's quite cemented by iron, and it gives to this horizon a very high bulk density, but also a cohesive behavior. So it's quite hard that water could penetrate through it. We have some names, let's say popular names that are quite common in Brazil, and I know that also quite common abroad, like Australia, Africa, and even some parts in Asia, that they call the petroplintic horizon as laterite, as kunga, or as iron stones. So all these three words, they just express what we in the soil science call as petroplintic horizon. Okay. Here are some photos of the petroplintic horizon. You can see a piece of it, and here you can see it in the field. So it's a piece, and here it's exposed. So I could not dig deeper than 50 centimeters because definitely I could not dig in this petroplintic horizon just because of that. The criteria to identify and classify a petroplatintic horizon are quite simple. It consists of oxymorphic features. So it's formed by iron oxidized, goethite, and hematite in the majority of cases. And these features are inside soil aggregates that are at least partially interconnected and have a reddish, yellowish, or blackish colors. And it should register at least 2.5% of iron content that is extracted by ditonite. This ditonite, it's bicarbonate citratum ditonite. It's a specific method that measures the total iron content. So I will measure the total iron content, and it should be high because we are talking about a horizon which express iron cementation that was cemented by iron. Okay. The other option is find 10% more iron, total iron, in the oxymorphic features than the rest of the soil, expressing that iron is concentrated in some oxymorphic features, plintite, petroplintite, okay? And it has a ratio between iron extracted by ammonium oxalate and iron extracted by ditonite less than 0.1 in the fine earth or in the oxymorphic features. Why I'm saying that? Because I'm saying that I have a very, very low content of iron associated to organic matter and slash or low crystalline minerals. The higher content of iron, the majority of iron, it's associated to high crystalline minerals, okay? The petroplatintic horizon should be cemented with a cementation class of at least strongly cemented. So hardly you can break it with your hands, knife, shovel. It's quite easier to break it, not quite easier, but let's say it's easier to break with heavy machines, okay, some equipments. And it's continuous to the extent that vertical fractures, if we have these kind of vertical fractures, have an average horizontal spacing of 10 centimeters or higher than this and occupy less than 20% of the volume, okay? So if we have some vertical fractures, some cracks in this cemented horizon, in the petroplatintic horizon, these cracks, these vertical fractures, they are not quite common, okay? So at least they have a distance between 10 centimeters between them. And it does not have coarse roots except in the vertical fractures. So the roots cannot easily go through this petroplatintic horizon except along those vertical fractures, along these cracks, okay? And it has a minimum thickness of 10 centimeters. So I should register at least 10 centimeters of the cemented iron cemented horizon to identify the petroplatintic horizon. And we also have the piezoplantic horizon. The piezoplantic horizon, it is formed by the destruction of a petroplatintic horizon or because an incipient or low cementation, okay? So I still register a high content of iron and manganese nodules that are quite difficult to break them, but now they cannot form a continuous layer. So I cannot see like this, that express that I don't have space enough to roots grow through this horizon. Now I can see that we have a lot of iron. All these pebbles that you can see in this photo are pieces of petroplatintic materials that are cemented by iron, but they are not forming a continuous layer, a connected layer. You can see that roots can easily grow through this horizon because I have iron concentration, sometimes also manganese concentration, but this concentration does not form a continuous layer, okay? I see that water and roots can penetrate through it. As I said, some people said that this piezoclintic horizon is formed by the wafting of a petroclintic horizon. So after formation of a petroclintic horizon, some process could start to broke it, and after some intense wafting of this petroclintic horizon, I can register a piezoclintic horizon. And also some people also said that the piezoclintic horizon can be one step before the petroclintic horizon. When we have some cementation, but the cementation is not strong enough to create a continuous petroclintic horizon, okay? A continuous cemented horizon by iron, okay? So here are some of these pebbles that you can see. They are quite hard, quite heavy. And if you broke it, you can see soil cemented by iron. We can see some quartz crystals inside this pebble. And the criteria to identify a piezoclintic horizon, it is composed by mineral material, so the organic carbon content should be less than 20%, and at least 40% of its value, it's composed by single or combination of concretions or nodules. Okay, these concretions or nodules, they are iron cementation, iron concretions are on nodules like this one. This is a nodule, okay? These are nodules or concretions. The difference between nodules and concretions is the internal fabric. When we have a concentric internal fabric, we have a concretion. If we don't have a concentric internal fabric, we have a nodule, okay? So in this case, we have a nodule. And these nodules, they could register yellowish, reddish, or blackish colors, expressing iron and or manganese concretions and cementations, okay? These concretions and these nodules cannot be broken by a knife, hand, shovel. They are quite hard to be broken, okay? For example, to broke this piece, I used a hammer and hit it like a lot of times to then could break this material. They cannot be easily broken, okay? Another option, it remains of a broken petroclintic horizon, okay, with a diameter that's higher than 2 millimeters and a cementation class of at least moderately cemented, okay, so pieces of this petroclintic horizon, and does not form part of a petroclintic horizon. So I cannot register petroclintic and piezoclintic horizons at the same time, just one of it. And I should register a minimum thickness of 15 centimeters, a little higher than the petroclintic. That's just 10, okay? And I also could register the plintic horizon. That's also one step before the petroclintic and piezoclintic horizons. The plintic horizon, it registers some redoxymorphic features, and it is not cemented by iron and or manganese, okay? So the plintic horizon only shows you that that specific depth it's suffering or suffered in the past some oscillation of the water table level. So the water table level increase or decrease, go ups and down, and because of this change, we change the E age, and the change of the E age changed the valence, the state of the iron and manganese. So the iron and manganese starts to be reduced and oxidized, reduced and oxidized. And then when they reduce, you register a grayish color with some nodules and concretions and what we call plintite that are these reddish spots, they express the oxidation of iron when the water table level goes down. So the oscillation of the water table level will change the state of iron when iron starts to oxidize because the water table level goes down. Then you create some of these spots that we call plintite. These plintites express that this soil suffered in the past, in the last years, for example, or the last months, some change of the water table level. And because of this, we have some change of iron state between iron 2, iron 3, iron 2, iron 3. They change a lot of time. And we don't have any cementation yet, okay? This could evolve in the future for cementation, but it takes time to cement some horizon, okay? So this water table level should fluctuate for several hundreds or sometimes millennium of years to create petroplintic or pisoplintic horizons, okay? So you can see here very easily these reddish colors associated to oscillation between oxidation and reduction of iron. So let's see the criteria to identify a plintec horizon. It has mineral materials, so the organic carbon content should be less than 20%, and it has 15% of the exposed area with oxymorphic features inside soil aggregates that are black or have a redder hue and a higher chroma than the surrounding material. So both cases, especially this one, you can see this reddish color, and it's much reddish than the overlying horizons, okay? Expressing what we call oxymorphic features, features expressing oxidation of iron, okay, because of the fluctuation of the water table level, okay? And it should register one or more of the following: a high content of iron, total iron, okay, so at least 2.5% of the iron extracted by citrate, bicarbonate, deuterite, and it should register, it should register 10% of more of iron in the oxymorphic features. So these oxymorphic features that express iron concentration, it could register a high content of iron too, and I can analyze them. Some of these oxymorphic features change irreversibly to a continuous cemented horizon with a cementation class of at least strongly cemented after repeated drying and wetting. So I can took a piece of this horizon and I get it wet and dry in the lab. Okay, so I can wet that horizon and then dry. Wet, dry, wet, dry. After these repeated drying, wetting cycles, I can realize that now the horizon start to be cemented by the iron that's now cementing this horizon. This also could be something that allows you to identify the plintec horizon. Another option is has a ratio between iron extracted by ammonium oxalate and iron extracted by citrate, bicarbonate, deuterite of 0.1. Again, the higher content of iron should be connected to high crystalline irons or iron oxides, not low crystalline iron oxides, no organic matter. Okay. And this plintec horizon does not form part of a petroplintic or pisoplintic horizons. So I cannot combine them, okay? The plintec horizon is a step before the petroplintic and pisoplintic because it does not register strong cementation in the field, okay? And the plintec horizon should register a minimum thickness of 15 centimeters, okay? Now let's see one step before the plintic horizon, the ferric horizon. The ferric horizon will register more reductive features than the oxymorphic features. So now we have more reduction than oxidation. So the iron are just starting to be oxidized, okay? So we have some water table fluctuation, but the water table stills high at the majority of time. So the soil has more grayish color than reddish and yellowish colors or dark colors. So it seems that we have some oxidation, but the oxidation is quite incipient yet. Okay, so let's say that it's the first step. Okay, we don't have any correspondence of the ferric horizon with soil taxonomy. So we don't have this kind of horizon in soil taxonomy. They just don't classify. The pisoplintic and the petroplintic and the plintic horizons, all of them, we call it oxic horizon in the soil taxonomy. So three horizons, they are composing only one in soil taxonomy that we call oxic horizon. In the case of the ferric horizon, we don't have it. Okay? So the criteria for the ferric horizon is that it's mineral material. So the content of organic carbon it's below 20%. And this ferric horizon consists of one or more of subhorizons with one or both of the following. 15% of the area it's occupied by coarse masses inside soil aggregates that are black or have a menstrual color hue rather than 7.5 R and a chroma equal or higher than 5. So we have some material inside the soil with reddish or black colors, okay, but the minimum is 15%, or 5% of this area it's occupied by concretions and sorry, concretions and or nodules. Oh, sorry guys. So we have a very low we have a very low area area that has no concretions or nodules, okay? So as I said, it's a very beginning, it's an early beginning of this change of a reducted environment to an anoxic condition, to a condition that now iron starts to oxidize, okay? And of course, the ferric horizon cannot be a petroplintic, pisoplintic, or even plintic horizon. And the minimum thickness is 15 centimeters. So I can register some iron concentration, but a very low content of iron cementation, and definitely no no cementation. Okay, so no cementation of the horizon. And we have another option of a horizon that also register a high iron content. That is the ferralic horizon. The ferralic horizon is equivalent also to the oxic horizon in the soil taxonomy. So the ferralic horizon is a horizon that expresses an intense warping and leaching. So we have a high content of iron, but now the iron it it is not suffering oxidation and reduction, oxidation or reduction, or even it does not suffer it. It did not suffer it in the past for this kind of cycling of reduction and oxidation. Okay, the iron in the ferralic horizon it's concentrated because the iron could not be destroyed easily when iron is composing goethite and hematite. So In the case of the ferralic horizon, we have an intense destruction of primary minerals. For example, feldspars, olivine, plagioclase, pyroxene, and destruction of these minerals release some iron, and then the iron was converted into iron oxides, goethite and hematite, especially these two minerals. And these two minerals can be hardly destroyed. So because of the intense destruction of primary minerals, you have a high content of iron composing goethite and hematite as secondary minerals, and they are not cementing the soil. They are just produced by warping and leaching, and they have clay size, the majority of them, and they compose the pads and the aggregates, but they are not cementing any layer. So now we have, let's say, a relative iron concentration. In the cases before, in the previous cases, all of those cases, we have an absolute concentration of iron. The iron was reduced in flooding conditions, and because of the water table fluctuation, the iron migrate and concentrated in some zones, and this absolute concentration of iron produces some cemented horizons, or at least some horizons that express darkish and reddish colors. In the case of the ferralic horizon, we have this iron concentration in a relative way. Because of iron cannot be easily leached, so you increase the content of goethite and hematite because all other minerals was intensively destroyed. Okay, so a deep warping and leaching destroyed all the other minerals and create a ferralic horizon. Okay, it's quite common that the ferralic horizon is composed basically by kaolinite, iron, and aluminum oxides like goethite, hematite, gibbsite, kaolinite, halloysite. Okay, because these minerals are some of those minerals that has a highest resistance against warping. Okay, let's see the criteria to identify a ferralic horizon. A ferralic horizon is composed by mineral materials, so the organic carbon content is below 20%. It registers a texture of sand, loam, or thinner than this. So I cannot register a sandy texture in a ferralic horizon, and the minimum content is 8%. It should register less than 80% of coarse fragments, piezoclintic concretions or nodules, or remains of a broken petroplintic horizon. Okay, and they should register less than 2 millimeters. Okay, so these fragments, they should be less than 80%. The CEC per clay should be quite low, should be less than 16 centimole charge per clay, by kilogram of clay. Okay, so when I split the CEC by the content of clay, the result should be less than 16. This is showing us that the ferralic horizon registers low activity clays. As I said, dominance of kaolinite, halloysite, gibbsite, hematite, goethite. I definitely cannot see 2-to-1 minerals. I definitely cannot see high activity clays, okay? Because ferralic horizon express an intense chemical warping and leaching, okay? This ferralic horizon also registers less than 10% of easily warpable minerals that compose the fraction between 0.05 and 0.2 millimeters. So the fine sand and the silt fractions could be not composed by a dominance of easily warpable minerals. So I can find some feldspars, I can find some muscovite, but they should be in a low quantity, in a low amount. Okay, I cannot find a lot of olivine or pyroxene because these minerals they should be destroyed to create the ferralic horizon. Okay, the ferralic horizon could also not present endic or vitric properties. These endic or vitric properties we already saw when we talk about those horizons that express ash, especially ash. So these materials, they are connected to low crystalline minerals and low wafering. So I cannot see any kind of allophane or immogolite in ferralic horizons. And the minimum thickness to identify a ferralic horizon, it's 30 centimeters, okay? Why we register a higher minimum thickness in this case? Because these horizons, they commonly are quite thick. And when I say quite thick, I say some meters, okay? So I read described ferralic horizons with more than 6 meters, but I heard and read articles that describe ferralic horizon with more than 30, 50 meters, guys. So this is just the ferralic horizon. I'm not talking about the entirely soil. Okay, so they commonly are quite thick. Okay. Okay, guys, before we keep going, I will stop a little bit so I can drink some water. You can go to a restroom, and I also can turn on my computer, at least turn the charger, okay? We will return in 20 minutes, okay? So let's return at 10:53 for, in my case, in GM3 minus 3, okay? In 20 minutes. See you.
See you, see you. Okay.
Democracy, please, can you mute your mic?
Okay, guys, let's return. Just open here again. Okay, let's return to lemonic horizon. This lemonic horizon, it express some iron concentration, and in this case we have some iron that comes from ascending groundwater. So some groundwater that it's in a water table level in a very deep horizon can ascend, especially in dry climate conditions, and this could bring some iron and create, as you can see here, this reddish or yellowish horizontal horizons, these colors that express some concentration of iron by ascending water. They have this horizontal shape that it's quite interesting to see because it's quite connected to the water table level. Okay, and you can see that they express this water table levels at different times. Because of this addition of iron, it could express some partial cementation. Okay, and this lemonic horizon, it has some specific criteria for identification too. So first of all, at least 50% of oxymorphic features, black surrounded by light colored materials. Okay, they should register a muscle color hue of 2.5 units rather, and a chroma that's one or higher chroma units higher moist than the surrounding material. So it should register stronger colors than the surrounding materials, as you could see, or have a muscle color hue 2.5 units rather, and a chroma that's one equal or higher unit higher moist than the matrix of the directly underlying layer. And the oxymorphic features are one or both of the following. They occurs predominantly on biopore walls, and if soil aggregates were present predominantly on or adjacent to former aggregates in the walls of the aggregate surfaces, okay, or underlain by a layer with 90% by area of reductimorphic features, I'm sorry. The way that we call it then in soil taxonomy and WRB are different. We just call oxy or reduximorphic features in the soil taxonomy, and here it should call oxymorphic or reductimorphic. So we have different words for them. Reductimorphic features that have the following muscle colors: when moist, a hue of N, 10Y, GY, GP, GB, or PB. Wow. Or a hue of 2.5Y or 5Y and a chroma that it's equal or below 2. Okay, so we must register colors that express reducing features, okay? It registers a cementation, a weak cementation, at least moderately cemented, and it should register a high content of iron and manganese extractable by bicarbonate citrate ditionite, so a high total iron and manganese contents that are related to iron and manganese oxides, and a minimum thickness of 2.5 centimeters. Okay. Another horizon that also expresses a strong influence of water table level, it's the stellic horizon. This stellic horizon expresses lateral iron concentration. So some water could migrate and achieve the water table and creates a perched water table. And when this water table migrates laterally, horizontally, it could get out, could had some springs, and this spring could induce some oxidation. Okay, so for example, we have in this case, in this photo, this hue and an impermeable layer here that avoids that all the water achieve the regional water table. So because of this impermeable layer, you create a perched water table, and this perched water table induce a lateral movement. When this lateral movement achieves the soil surface, so you have a spring. And because of this spring, now we have some oxidation here forming the stellic horizon. So you can see here, for example, that we have here a very dense horizon. Okay, this case is a natric horizon, and this natric horizon, above of it, we have this horizon that has some flooding conditions because of the perched water table. And because of this, we have some iron oxidation and reducing colors at the same time. But now this water, this perched water table, is not connected to a directly layer that avoids in this position the water penetration. In this specific case, we are talking about water that migrated horizontally, and now the water is getting out with a spring. Okay. So the criteria to identify a stellic horizon is that you need to register a high content of iron associated to low crystalline minerals, so at least 1% of iron extracted by ammonium oxalate. When I split the content of iron extracted by ammonium oxalate and iron extracted by ditionite, they should register a value of 0.5 or higher than this. I should register more iron associated to ammonium oxalate than aluminium. Okay. It should register a muscle color chroma of equal or higher than 4. Does not show reductimorphic features. So I should register concentration of iron. Does not form part of a limonic or spodic horizons. So I cannot combine these two horizons. And the minimum thickness is 5 centimeters. Okay, so it is a horizon that we have some iron concentration because of the lateral movement. I'm quite sad because I never saw this horizon yet. Okay, so no, actually, yes, actually, no. I just saw the limonic. I'm sorry. So this horizon, I never saw it yet. So I'm quite excited to see one and have photos. This photo I took from a book for you guys. But what I can say to you is that at the horizon connected to a slope and an impermeable layer in a subsurface horizon that create the spurted water table and induce some lateral movement. Okay, so when we think about iron-rich diagnostic horizon, we have a lot of them, and then each one has a specific properties. We have the petroplintic horizon, that's a deeply cemented horizon and low frequency of roots and voids. We have the piezoplintic horizon with a higher frequency of nodules and concretions, and it's permeable. We have a higher frequency of roots and voids because it is a broken petroplintic horizon. Okay, we have the ferric horizon that express the presence of mottles and or nodules concretions, but a dominance of grayish colors. We have the plintic horizon that express a higher iron tree content and a higher minimum content of nodules than the ferric horizon. So the oxic conditions are dominant, not the reduction conditions. We have the ferralic horizon, which express a concentration of iron tree, but now it's a relative concentration of iron tree. The destruction of other minerals release iron, and then this iron is composing goethite and hematite dominantly, and because of the intense buffering and leaching, we have uh, a high content of iron. We have this limonic horizon that express concentration of iron because of the ascending groundwater, and we have at least weak cementation. This iron is concentrated in the biopores and walls of the voids. And we have in the last option the cetallic horizon, that's a lateral iron tree concentration. So you can see that all of them register high concentration contents, a high iron contents, and they express concentration of iron, but they express at different levels, and especially because of different mechanisms, because of different process. Okay, we have the petroduric horizon. It's totally different from the others. This horizon express cementation of the soil, but now cementation by silica, and it's quite common in dry lands. Okay, this was one of the horizons that I could saw in this last field work that I did last week. So nice. Unhappily, I didn't have time enough to show you the photos here, but I can send to them later. They are common in dry lands. Okay, and the petroduric horizon, it's similar to what we call duripen in the soil taxonomy. The petroduric horizon, it's a horizon which cementation of silica fulfill almost all of the voids of one specific section of the soil, and because of this we have a strong cementation. It's quite hard and difficult to break this horizon with a knife, a shovel, and even sometimes with heavy equipments, because the silica it's quite strong. Okay, so it gets this kind of whitish color that you can see here, and sometimes some darkish colors, but the whitish are more common, and this whitish colors they came from the silica, and the silica promotes a very strong cementation. The petroduric horizon it's formed because of high pH at the surface. So as I said, they are formed in dry lands, areas that we have a high evapotranspiration, and this very high evapotranspiration could induce precipitation of salts. When starts to rain, the salts are dissolved, increase the pH at 8 or sometimes even higher than 9. And at this very high pH, the silica can be easily dissolved. So a lot of aluminum silicates are intensively destroyed because of the high pH, even when we have a low wafering and low leaching, and the silica can migrate from the top to the bottom. When silica migrates, it could achieve a low pH. It could achieve a pH that's close to 6 or even 5. When the silica achieves this kind of pH, the silica reprecipitates as low crystalline silica, not as a new mineral. No, it's just as an amorphous material that now will fulfill the voids and cement that horizon. Okay, so sometimes in very dry conditions, you can see this kind of horizon expressing this strong cementation. Okay, here you can see some pictures, especially these thin sections and these thicker sections. All of them are petroduric horizons, horizons that are quite difficult to break because they were cemented by silica. You can ask, oh, JJ, how can I differentiate, for example, petrocalcic horizons and petroduric horizons? Because both are quite hard to break, and both register this kind of wettish colors. Well, you can just drop acid, because if you drop acid in a petrocalcic horizon, you can see the reaction, you can see the bubbles. When you drop acid in a petroduric horizon, no, you will not see any bubble, you will not see any reaction, because silica does not react with acid. Okay? Here are some thin sections described in petroduric horizons, and you can see these yellowish colors as this low crystalline silica that fulfills almost all voids of the soil. So you only can see voids here in this white zone, and here and here and here, here, but the majority of soil is fulfilled by silica and other materials. Because of this, we have this high bulk density and this strong cementation. So let's see the criteria to the identification of a petroduric horizon. First of all, it is a mineral material, so the organic carbon content should be below 20%. It should register at least 1% of a visible secondary silica as an accumulation, and we should register that when air dry, less than 50% of the soil slake in a acidic environment. So I put some soil, some pieces of this petroduric horizon in a solution with hydrochloric acid, and even after some time, this soil, or less than the 50% of the soil, will slake. Okay, the majority of cases we don't have any slake, but less than 50% will slake with acid. Okay, as I said, acid does not react with this silica cemented horizon. When air dried, more than 50% slake in hot concentrated potassium hydroxide or sodium hydroxide. Okay, and at least if I alternate with hydrochloric acid. Okay, so potassium, sodium hydroxides, yes, they will dissolve silica because of the high pH that they promote. So when I put some pieces of this petroduric horizon in contact with hot concentrated potassium or sodium hydroxide, so then I will some slakes, so I will start to be destroyed. Okay, and if cemented, it is cemented, okay, at least partially by secondary silica with a cementation class of less, at least weakly cemented, both before and after treatment with acid. So I should register that the soil is strongly cemented and cannot be easily destroyed by acid. It register continuous, it is continuous and eventually has a vertical fractures, and these vertical fractures, they are not quite frequent, so at least 10 centimeters of distance between them, and they occupy less than 20% of volume of that horizon, does not have coarse roots except those coarse roots that grows along the vertical fractures, and the minimum thickness of just 1 centimeter. Just 1 centimeter is enough. Okay? We have also the Duric horizon, so the petroduric and the Duric horizon. The Duric horizon also registers some cementation by silica, also is connected to the Duripan, and in this case, we see some silica nodules. So quite interesting. We already saw calcium carbonate nodules, we already saw iron and manganese nodules. Now let's talk about silica nodules, okay? So these kind of nodules, they can precipitate in the soil and form what we can see as the Duric horizon, okay? The Duric horizon, it registers at least 10% of nodules and compressions of this material, so remains as a broken up petroduric horizon. So you can think about the Duric horizon as the piezoclintic horizon composed by silica. So we have the petroduric. If the petroduric starts to break, the Duric horizon. Okay, at least 1% of accumulation of secondary silica, and the same when we mix this material with acid, we have a low destruction of the material, less than 50% slags. When we mix this soil with potassium hydroxide or sodium hydroxide, so then we have a strong destruction, so soil starts to slake, at least 50% will slake. We have cementation of this material, okay, so they should be hardly cemented, and a diameter of these nodules and concretions of at least 1 centimeters, and a thickness now of 10 centimeters. So the thickness is 10 times higher than the petroduric, okay? We also have another horizon that also express some hardness, but in this case, it's not cementation, but a high bulk density horizon is the coesic horizon. Okay, the coesic horizon, we don't have accumulation of matter, but it's more related to organization of particles. In this case, we have some restriction to drainage and root growing because these horizons are quite rich in kaolinite and poor in iron oxides and soil organic matter. So the kaolinite has a layer feature, a layer shape, and you can combine or you can put one kaolinite above the other one, above the other one, above the other one, and because of this, the voids will be not connected. And because of this low connection between voids, the water percolation through the soil and the root growing will be quite hard, okay? This coesic horizon is quite common in the tropics, especially in soil formed by kaolinite-rich materials in very well developing environments like wet and tropical climate conditions, and poor iron poor parent materials, okay? The coesic criteria, coesic diagnostic horizon, I'm sorry, has some criteria. The content of organic carbon should be low, as I said, so less than 0.5. It should register a high content of clay, so at least 50% of clay. It should register a low CEC per clay because the dominance of kaolinite, as I told you, So if you split CEC per clay, should be less than 24 centimole charge per kilogram of clay, and has a single or a combination of some structures, massive structure or a weak subangular blocky structure. This horizon, it's not cemented, and when dry, it's quite hard. It's quite difficult to break it. Okay, and I think that this is the most important difference between the coesic horizon and the others. Because when you talk about, for example, a petroduric horizon, you have also a hard resistance, so you cannot easily break it with your knife, hands, or shovel. But a coesic horizon, when you put water, when you put some water in this horizon and it gets wet, it could be easily broken by your knife. You can easily remove some pieces with your hand or a shovel. So the coesic horizon, it's quite hard when dry, but it's quite easy to break it when it is wet. It's different from the others. A petroduric horizon cannot be easily destroyed when wet, when it is wet. Okay, it's wet and no problem. The silica cannot be destroyed by just water. But in this case, the coesic horizon, the water penetrates between the minerals and reduce the resistance of it, so it can be easily destroyed. But when it's dry, wow, it's quite hard. It's quite difficult to break it. Okay, and the thickness of the coesic horizon is at least 10 centimeters again. We have the Fragile horizon. The Fragile horizon, it's one step below the coesic horizon. So we have some adhesion, we have some bulk density, high bulk density, and because of this, the roots starts to grow laterally, but it's not so intense as the coesic horizon. So no accumulation of water or of matter. So we also have some restriction to drainage and root growing. It also is rich in kaolinite, poor and iron oxides and soil organic matter. So the criteria is different because now we have a less intense uh, less intense adhesion of that horizon. So the fragile horizon, it has 60% of prismatic, columnar, angular, or subangular block structures that without coarse roots, okay? And when they have these coarse roots, the spacing is equal or higher than 10 centimeters. Show evidence of some soil formation, so I can see some horizons, okay, some pads. The soil material in between the soil aggregates and 50% or more of the volume aggregate are not cemented, so no cementation again. The non-cemented parts do not cement upon repeated drying and wetting. So if I took a part and I get that soil wet and dry, wet and dry, wet and dry, so no cementation could be registered after that. The non-cemented aggregates parts have a brittle manner or feather and a ruptured class moist of at least firm. So I can register that again. If I get it wet, I can see some destruction. Okay, less than 0.5% of soil organic matter. And of course, I cannot see any kind of efferency with acid, and a minimum thickness of 15 centimeters. Okay, so basically I have a less cementation now. I'm talking about the cementation when moist, but not a cementation. No, I'm sorry, guys, it's not the word. Hardness. I have a hardness that when's wet, I can realize that's hard to break, but it's less harder. Okay, now. And when it's dry, I can see some evidence of material that's harder to dry, but with less hardness than the coesic horizon. The gypsic horizon, now we have some concentration of gypsum. We also have this gypsic horizon in the soil taxonomy, and we express the concentration of gypsum the same way. because of the dry conditions that concentrate calcium sulfate, tidal water that could be enriched in calcium sulfate, and this horizon it's not cemented. Okay, it registers usually this whitish color because of the gypsum. What? Go. And the criteria is that they register at least 5% of gypsum. Uh, this horizon should meet the diagnostic criteria for protogypsic properties, that basically some secondary gypsum that's precipitated, a gypsum content that's 5% higher than the underlayer horizon, and no lithic discontinuity. So I should register higher gypsum content than the underlying horizon. Has a product of the thickness times gypsum content of 150. So I should multiply the thickness and the gypsum content, and the result should be equal or higher than 150. This gypsum horizon does not form part of a petrogypsic horizon. It's a cemented horizon, a horizon cemented by gypsum, and a minimum thickness of 15 centimeters. The petrogypsic horizon, it's a strong precipitation of gypsum, and then the gypsum now fulfills all the voids, and because of this, you have a strong cementation. This strong cementation creates a horizon that's quite hard to break. It's cemented by gypsum. You can see some photos like here and here. All of these materials, they are enriched in gypsum. So at least 40% of gypsum and at least 1% of secondary gypsum. And of course, cementation, some vertical fractures. If you see some vertical fractures, they should have a space between them of at least 10 centimeters. So the distance between them of at least 10 centimeters. I does not register coarse roots except in these vertical fractures, and a minimum thickness of 1 centimeter. Okay. We also have another horizon that's also cemented, now cemented by calcium, the petrocalcic horizon, cementation by calcium carbonate. It's the evolution of the calcic horizon, okay? And you already saw this picture because we saw the same horizon in the soil taxonomy, the petrocalcic horizon, expressed cementation by calcium carbonate. And what we have, a strong effervescence reaction after addition of some hydrochloric acid. So if I drop some hydrochloric acid in this horizon, I will see some reaction, some bubbles. This horizon should register cementation by secondary carbonates. I can see in some cases some vertical fractures. If these vertical fractures are present, the distance between them should be at least 10 centimeters, and they should occupy less than 20% of the horizon, so a low frequency. They does not have coarse roots, except if these coarse roots are growing through the vertical fractures, and they register a minimum thickness of 1 centimeters or 10 centimeters. 1 centimeters, if 1 centimeter, I'm sorry, if it is laminar or and rests directly on continuous rock. So if I register this petrocalcic horizon above the R layer, okay, if I register this case, just 1 centimeter. But no, I can see the petrocalcic horizon, and above and below it, I can see a C horizon, so or another B horizon. So in this case, will be 10 centimeters, the minimum thickness. And we also have other horizons that does not express accumulation of material, that are not related to humans, they are not organic or mineral, they are not organic, and they are mineral materials, okay? In this case, I think that it's better that we keep for the next class, because we already have a lot of things to worry. Okay, we saw a lot of horizons today. I already shared the document for the exercise of classification according to WIB. Of course, pay more attention to the surface diagnostic horizons. You can try to classify according to the subsurface horizon too, but for now, at least pay attention for the surface diagnostic horizons. The answers are there too, so please pay attention for this. And next week, we will finish the diagnostic horizons, the subsurface diagnostic horizons. So I will share a list, a new quite a set of exercises asking you to identify also the subsurface diagnostic horizons according to WRB, but only in the next week. For now, if you pay attention for the surface, will be enough for me, okay? I already add the answers in the end of this exercise so you can see and check about soil classification, okay? But as I said, next week I will share a new set of exercises so you can classify them, okay? Guys, before we leave, I need to ask you another thing. I'm going to talk about the field trip to this afternoon with the chair of the department. But for that, I need a list of names of people that plans to attend the meeting. Okay, attend the field trip. I'm sorry. So please, if you plan to attend this field trip, just let me know by mail. So send a mail to me and just said, oh, JJ, I plan to attend this meeting. I plan to attend this field work. I'm sorry. And then I have a list of names. And because of this, I can talk with him about which kind of transportation we need. If we need a bus, if we need a shuttle, if we just need a car, will be much more than enough. But I need to know how many people plans to attend the field execution. Okay,
Okay.
guys. Any doubt? Do you have any
Yeah,
doubts?
Professor, and video class 10, I think not full. 10 minutes video.
Okay. I will check what could happen. As I said, last week was quite difficult because I had some internet problems. I think that the connection was not good in the hotels, and I will check. Okay, I will check what could happen and remove the video and upload the entirely video. Okay, I will try to do this afternoon.
Okay.
Okay, also send the slide.
Oh yes. The
Send,
last
send.
slides I will put these ones and the others. Okay, I think that I finished it in the 7th class. Now we are in the 9th, so I will share the slides. Don't worry.
Okay.
Thank you.
Welcome. So, any doubts?
No, it's okay.
Okay, great, guys. So see you next week, and I will share the slides and check the video. Okay. So,
Okay.
see you guys. Bye bye.
Ciao. Ciao.
Ciao.
Ciao, ciao.
Ciao.